Good evening. It's a magic place here, this stage, very, very historical. Because I remember when I was little and short, I was sitting there and watching to the famous artists here on this stage. Erosi Manjaladze, Ramash Chikwadze, and right now I'm here, I never imagined myself to performing here. And the presentation, what is presentation? It's not knowledge transfer. This is the theater, one art theater, and I'm performing here. And the souls, their souls are watching on me, what I'm doing. I will do my best. So, yes, I would like to send my big thanks to Natia and Becca to invite me here, and what they're doing, it's absolutely amazing, and I wish them continuation, and continuation. Now about me. My name is Alexander. I'm Georgian. I'm working at CERN. CERN is the European Organization for Nuclear Research, which is situated in the border of France and Switzerland in Geneva. And at the same time, my affiliation is the Georgian Technical University, so I'm professor there. And today I'm going to talk with you about the digital design technologies. I would like to apologize because my presentation contains a lot of text, and might be it will be annoying you, but I try to jump over those slides. And this is mostly the technical presentation about the technology of this digital design. Digital design, okay. We all using this term of digital design, and it's the different various fields of the implementation of the design, like the style design, like the engineering design, mechanical design, like the simulation, prototyping, visualization, development of the three-dimensional scenes, the digital avatars and 3D scenes from the metaverse for the virtual reality, etc., etc. There's some example, for example, stylish design, which is two-dimensional design for clothing and so for tattooing, but on the right side, this is the stylish surface design for the automotive design and the plane design, which are from the NURBS, and this is very much free design. And the mechanical engineering, like the CAD/CAMs, computer-aided design, computer-aided manufacturing, from the generic design to the computer-aided design, and going to the CNC machine, which is the CAM, computer-aided manufacturing. The analysis and simulation and finite element analysis methods on the left side, and the DMU, the digital mock-up analysis of the integration, conflict checking, etc. Architectural design to examine the civil engineering infrastructure internally and externally, and to make some evaluations. And this is the rapid prototyping. The image on this side, this is not Photoshop, let me tell you. This is the real facility. Designer equipped it with the special lens, and he or she, I don't know, who is he, watching to the design and the 3D printing and stereolithography and the service design, digital avataring, and etc., etc. So, all these design activities has the common platform, which is the geometry modeling. Finally, it comes up to the geometry modeling. And this geometry model is existing in the memory of the computer somewhere. So this is very much digital model, and that's what I call it, the computer-aided three-dimensional digital modeling, CA3DDM. This is my terminology. Might be wrong, might be not, who knows. And today I would like to talk with you about the challenges of the CA3DDM, which is written here. This is migration, integration, simplification, visualization, and finally break the silos. At the end, if I came up to the last topic about the migration, What is this? If I'm single designer and I'm working with the one single project, everything is fine because this is my style, I know what I'm doing, I have my platform, I have my methodology, etc. I'm generating the project and the customer is very, very happy. But what's happened if there are some other designer also working with the same design, and this is the collaborative design, and then the problems are rising, and the migration came to this game. First of all, about the collaboration. Nowadays, all design projects are collaborative design. You see here the one example of the collaborative design, which I'm involved in this project. This is the Atlas detector. You don't know for sure what's this, but this is the huge geometry model, let me tell you. Take a look to those pictures. 47 million geometry primitives inside, millions of the parts, and thousands of the assemblies, and the huge collaboration who are design Atlas detector facility. 178 collaborative partners, 9 design organization, and all are developing and designing this huge guy. And here it is, problem of migration. Why? Because everybody used the different platforms for design. Those platforms are not synchronized. They are not talking with each other. And this is the natural, because they are built on the different kernel libraries, and they interpret the geometry differently. Even if designer using the same platforms, might be their design is different. And finally, it should come into the one platform. It means that the geometry should be transferred from the one platform to another. And this is the problem of migration. And you see some case studies here. For example, the one study about the Airbus A380, this production of this airplane was postponed for 1 year because of migration process, because the models were migrated from CATIA V4 to the CATIA V5. It's the same platform with the different versions, but it costs the huge work. And Daimler-Benz, for example, spent 255,000 models and involved the 300 designers to make the migration. And this last one is our case study. It's me and my team who were involved in this activity. During the 2.5 years, we are migrating the Atlas detector geometry from Euclid to the CATIA, and it takes the 13,000 man-hour, and 3,700 geometry models were transferred. So this is the huge problem. And also here it's indicated that when you are transferred the geometry, you lose the accuracy. Let me hide this, just only look to the last percentage. 40% was failed. The geometry was failed. It needs the reproduction. So this is the very bad. Geometry integration, another thing. When the designer make his design and he submit it to the entire design, it should be checked on the integration. Might be the design has the integration conflict checking. This is the overlaps. This is the contacts. This is the clearances, which we call the static conflicts analysis, and also dynamical conflicts analysis. You see this video, it's done by me. It's not professional camera, it's me who was filming this. This is the process of the installation of the so-called end cap toroid magnet in Geneva at CERN. It takes place there. This is the very, very huge monster with the 280 tons, should be lifted down or 100 meters under the surface. And it's impossible to put it just like it is. You have to check the integration dynamical conflicts, which we have done. This is our team from Georgian Technical University. We just model it and check the integrity of the installation path. And by the way, this is not just only lifting down vertically. You should move this guy alongside a little bit, then vertically, horizontally like that, and the guy is shaking, vibrating, and so this is the tough problem. You see here, it's quite the very, very small gaps. You should know, take account these gaps and other gaps as well. We model it, and we find out, by the way, the clashes. Nobody at CERN was trusting us. Some people saying that, oh, the Georgians are playing the three-dimensional games, don't trust them, and etc., and etc. But finally, they make the laser checking, and they prove that we were right, and they disassembled those chambers, and it postponed the installation process for 2 weeks. So we are good. So now, thank you very much. So now another challenge is the simplification. Okay, we have the good geometry, we finally migrate everything, but the question is how to use it. Because this is very huge geometry, and question how we can use it. And it looks like that you cannot take this geometry and use somewhere in your particular projects without simplification. And simplify it means that you have to remove something. But if I remove something, it depends. For example, for the engineering simplification, here I have this nice guy. You see, this is the liquid argon pump inside of the Atlas detector, and on the right side you see the simplified one, which is using for the integration conflict checking, because it's removed internally is nothing, the externally it's ironing quite well. And another thing is the simplification for the simulation. Okay, let me skip it. Okay, let me also skip it and go back to the visualization. Oh, visualization is very, very, very challenging thing. I mean, design geometry for the visualization. Here we have some practical implementation. By the way, all these terminology is our terminology. For example, ART. What is the ART? If you start searching into the Google will say nothing to you. And ART, this is augmented reality tools when you have the mobile phone, and through the mobile phone you can put your geometry on the table for the discussion. Also ARD, the augmented reality door. When I'm traveling with my mobile phone, I have the scene, I'm watching to you, and also I'm watching the door, virtual door somewhere here, and inside of the door I'm watching something is placed there, and I'm moving and going and entering this door, and I feel not in this theater, but I feel myself in the different environment, and I start navigating and watching what's there. There is another door, and I'm traveling. Be careful not to tackle with someone or somewhat. This is the ARD, and also LND, augmented reality landscape, when you are sitting in the cafe and you have the field and you want to take your mobile phone and you want to show your friends how big is your geometry in the real scale dimensions, and you see, oh, Atlas detector is almost like the Eiffel Tower or whatever. And the ARB, everyone knows what is this, ARB, augmented reality book, and so and so. And what about the scene? For example, you see, those two guys are playing the chess. Well, and this is the real scene, by the way. Only one fake thing is here, that this guy, who is the real, has the ordinary glasses, which is fake, really fake. But if he has some special glasses, everything is true. And this is true. If this guy equipped it by the Microsoft HoloLens, then this is possible. And also, if you have the Oculus Rift, and this is 100% true, nothing is fake here. We can play the table tennis. I love this game, and we can play like this. Everything is good here. Just only one small but. This is the price, and check these prices. By the way, when I'm preparing this presentation, I check the current prices, and I see that the Oculus Rift is now about the $400 US, and HTC Vive is about the 500. Comparing what was their price 1 year ago, the Oculus was about 600, and HTC was about the 700. So they decreasing, and this is the tendency it's going on. So it's decreasing, quality increasing, the price is decreasing. Unfortunately, HoloLens, a year ago, it was 3,500, and for the moment, this is the same. So, well, very good. Now about this challenge, quality against the performance. These are the two parameters which are very much dislike each other. I mean, if you want to increase the quality of your 3D scene, you will kill the performance. You will increase the load on your GPUs. Your application will be slower down. You increase the traffic of the downloading your geometries from the net, and etc. And you feel that what's the game it is, what's the application it is, you dislike it. You want faster application. In this case, you have to decrease the quality of the 3D scene, and your performance will rise. But then you watch with your HoloLens the scenes and in your Oculus, and you dislike because this is the low quality. This is a big problem. How to find the balance between the performance and quality. And one of the main factors who can find the balance between those two antagonistic parameters is geometry. How you design your 3D scenes. We call it fast geometry. This is our terminology. Might be wrong, might be not, but we call it fast geometry, so-called fast geometry. What is the fast geometry? This is geometry which helps us to find the balance between the performance and the quality. So I have both relatively acceptable performance and the relatively acceptable quality, and how to develop the fast geometry. This is a tricky thing. For example, this is the example. If we have the rounded, all this technical design, I have a lot of holes, you see here, and might be those holes are not visible, depending on my zooming rate. Might be they're very, very small, and I'm not able even to see them. But each hole provokes the facets. This dramatically raises the number of facets. A number of facets, it means that you have heavy geometry. But if you remove those holes, you will remove the facets, and your geometry becomes lighter, so it's going up to the balance. If you do this, and you see the difference. Also, if I have the rounded surfaces somewhere, you see the rounded surfaces there, and this is the same guy without rounded surfaces. And might be from the zoom factor, you never see those rounded surfaces, never see it, because of your zoom rate of your application. But they exist physically in the geometry, and they increase the number of facets. Just to remove, we have to remove it. Also, the approximation, the value of the approximation. All circle in the geometry is not a real circle. This is the number of vertices. If I want to see the high-quality circle, very smooth, I have to shorten the vertex. It means that I'm decreasing the approximation, but it's same time increase the number of facets. So, what is the optimal value here is depends of your scene, your 3D scene, for your object, for your zooming factors. Finally, this is the case study. Me and my colleagues, we are developing the three-dimensional model for the visualization application of the Atlas Outreach group. So they ask us for their master classes and their outreach activity to develop the mobile application to visualize this monster. As I say, there are the 47 million primitives, geometry primitives, thousands of assemblies, and millions of parts. It's impossible. No applications, no phones will visualize this. It should be simplified. How to simplify it? We did it according to the examples I already show you. And finally, look, result of our activity. From the about 30 million facets, which was in the original model, visualization model, we decreased less than 1 million. So we saved the 97% of the geometry becomes light, faster, Result are those applications. You see here, by the way, you can check right now this URL, and you will go to the framework, and you can testify this application in your Androids. You never need very superpower Androids. You can learn the Atlas detector. You can watch the physical events of collision, proton-proton collision inside. Oh, this, you see, its video was grabbed from my iPhone. This is virtual reality application running on my Android phone, which is very, very average quality and power, and you see it's quite high FPS. It's about more than 30 FPS. I know for gamers 30 FPS is nothing, just only starting from 60 FPS, but anyway, for this kind of application, it's quite well. And what is next? About the silo, I will very, very short with this. This is the last challenge I would like to introduce for tomorrow, for today. If we have the different departments inside the design office, the silo is that the people are very, very much separating. They have their platforms, they have their methodologies, etc. They're producing the geometry models, and those models are not speaking each other. This is very bad because it brings the duplicate geometry, a lot of geometry versions. It's incomplete view. It's hard for the update, and because the department has the different priorities, you cannot integrate it, and the good is the integrated approach when you have the one Bible geometry, let me tell you. This is the reference geometry, and you just transfer it to the different departments. So, if you are interested, this is the book. I wrote this book during the COVID pandemic, thanks to COVID, because it was only therapy for me, just sitting and writing the book, 500 pages book, which is ordered to me by the CERN community, and which is finally goes to the CERN library. By the way, you can pick it up from the CERN library, or even it's on the stage if some of you are interested. It's about there, with very symbolic price, 10 lari. Because I want to say to my friends tonight that I wrote the bestseller, which is selling. I'm selling my books. I'm good. And if you don't want to sacrifice 10 lari, then you can go to this link and download it electronically and learn much more about all this stuff, how to build the fast geometries, and etc. and etc. This is conclusions. You want me to read this? Or this? Okay. What is conclusion of conclusion? Everything which is existing is bad. Everything we are proposing is good. And the backup is that if some of you, I see the many young faces here, are interested to learn in depth the digital design technology, I'm inviting you to participate in the master's degree educational program at Georgian Technical University. This is the English program. You can study in depth the digital design technologies, and by the way, we have the collaboration agreement. It still continues with CERN, and all your dissertation will be on the thematic of the CERN. You will be somehow the part of the collaboration. I will give you some minutes for shots to just make shots of these important links, and later you can just check it. The first link about the NEC. NEC is Nuclear Engineering Center. The center I'm representing here at Georgian Technical University. The tracer framework is the application, the web-based application of the visualization of the Atlas detector. 3D Hub, this is our commercial side. If you want, some of you want to order us to develop the 3D models for the different purposes, CAD/CAM, the digital avataring, then you have to pay us, and we will do this for you. And also, this one is about the master's degree educational program. You can learn more, and as I say, from this link, you can download this book. Am I right? Is it good performance? Okay, see you.